if we're in R2, those components are referred to as the x and y components respectively. Notice I'm not using the word coordinates. I'm using components. These are the components of the vector. And that's so you don't confuse it with coordinates. Like if I tell you, hey, plot this point 3, 5, you go to the right 3 up 5 on a flat sheet of paper. Those are the coordinates of the point. If I say the components of a vector, that's just telling you like how much it goes over and up. There's no reference point to it. You're not starting, you can start from anywhere you want, right? In three-dimensional space, you have 3 components, the x, y, and z components respectively. All right, how do we add vectors together? Adding vectors is actually really easy, and visually some really nice things happen. So I'm going to show it to you visually first. And it's known as the parallelogram law. It works in both 2- and 3-dimensional space, but it's easiest to see it in 2-dimensional space. So I put here this important point when we add vectors together. It says if we add 2 vectors together, right, we take the tail of one of the vectors and paste it to the tip of the other. And the order in which you do that does not matter when it comes to vector addition. If you have 2 vectors, you want to add them. Let me get my 2 vectors here. Yeah, here we go. If I have 2 vectors and I want to add them together, remember, let's just put them here like this. If I'm going to add these 2 vectors together, this vector can go up, down, left, right, as long as I don't change its direction or length. This one can go up, down, left, right. When we add them, what I'm going to do, where's the arrow? Okay, sorry, the arrow's up there now. What I'm going to do to add these together is I need to take the tip of one of them, I'll take the tip of this one, and attach it to the tail of this one. So I can move this down and over like this. Okay, and I get something like that. Okay, you see that? The tip of this one is to the tail of this one. And so the answer is what does that give you when you add these 2 together? What should you get when you add 2 vectors together? A new vector. Where is that new vector here? Like where is it in my picture? I mean in this, it's like a hypotenuse almost. It's the vector that goes from here to here. It's like follow the path. If you move across here first, and then you go up, and you wind up here. So what's the result of everything? Is that you went from here to here. Okay? We call that the resultant vector. With me? Okay. That was me taking the tip of this one attaching to the tail of this one. Vector addition says you could do it the other way around. So I could have left this one alone and taken this one, moved it down and over like this, and had that, right? That should be the same answer. And you can see that what happens is you go here to here, and then here to here. So the result of that is really going from here to here, which is the same thing we just had. So the computer will probably let us see this a little bit better. If I take 2 arbitrary vectors, u and v, and I move them around, let me move the u vector, and I'm going to attach its tail to the tip of v right there. So I attach the tail of u to the tip of v. So the result is this. I would have started out through v, then gone up through u like that. The result is that I end up here, which is the same as starting here and ending there. I'm going to draw that vector in purple right here. Okay? Now, I could have done it the other way around, right? I could have moved the red one, right, instead. There. Sorry, what am I doing? I'm attaching tip to tip. That's not what I want, right? I want tail to tip. There we go. So which one should I move? Let's move the... Yeah, move u to the right. There we go. Okay. So you see, I attach them. I'm doing the u, attaching that tip to the tail of v. So I start here, go up and over, and I wound up, the result is that I just do this, right? These vectors are equivalent, right? Those vectors are equivalent because they're the same direction, they're the same length. So the result is the same. And let me do one more thing. Oh, I do have blue. Remember, remember the other thing that we had done, I believe, looked like this, didn't it? We had left the U one over here like that. That was the other way we did it. And so that's why they call this the parallelogram law. Because if you do it both ways, tip to tail, switch it, do tip tail with the other vectors, you wind up drawing a parallelogram, and then this result is the same.
Question.
Yes?
For the resultant vector,
The resultant vector.
have to be connecting arrow with arrow and one to the...
Yeah,
You understand my question, right?
I think I do. So whenever you add two vectors together, you attach the tip of one to the tail of the other, right? So where they're attached, ignore that. Ignore that. You're going to have a tail and a tip then, somewhere. The resulting vector is going to go from that tail to the ending tip. Got it?
Yeah.
But it doesn't matter which tip and tail you start with, like which ones you, for addition, for vector addition. All right, so this is just an example where we can just try and visualize this, like see if we can do it. And we're just going to draw on here. There's nothing to move around, so I'm going to have to try and draw it. So let's do V plus U. V plus U. So here's V, right? Here's U. Let's do V plus U. So I have to attach the tip of one of them to the tail of the other. Which one do y'all want to do? Which one do you want to leave alone?
We'll leave you alone.
Leave U alone, okay, and that means I need to bring V and bring it what? Up and over like that. So I attach the tip of this one to the tail of that one. So my V is going to wind up looking, and this may not be perfect, but it's going to be wind up, I don't know. Is that good enough? Maybe a little longer, but who cares, right? So that's my U plus my V, and now the resultant vector should start from the tail that I have here to the tip of this right here. That would be U plus V. So this is U plus V. Is U plus V the same as V plus U? Yes, it's commutative, right? Because it doesn't matter which order we do this. All right, what about U plus W? So let's leave U alone, right? Let's leave U alone again. Let's get W and let's add it to U. So I'm going to move up with W, slide it over like that. So move it up and over. What do y'all say? Oh, good enough? Yeah, that's perfect. I don't know what y'all are laughing about. Yes? That's U plus W. And now connect your vector that would go from the tail of one to the tip of the other one. So tail here to tip here, that would be U plus W. We following? Good? All right, I'm gonna erase those to do the last one, all right? To do the last one, I'm just kind of start over. So for the last one, if we want to do V plus U plus W, I'm gonna do the U, I'm gonna leave it alone, all right? Because it's right here in the center. I've got to move my U, or my V up here, which would do this one like we had just a second ago, right? That's my V. And then I have to add W, so I'm going to attach the tail of this to the tip of where we just were. So it's like we go here, here, and then the W. Another perfect W. What's the resultant? Starts at the tail of U and goes to the tip of W. That's the result. Now you no longer have the parallelogram law when you have three vectors like this, but you can see what the resultant is, right? All right, we're going to move on. This is just to make sure you understand the geometric idea of adding vectors together. All right. Adding them visually is one thing. Adding them algebraically is even easier. Because if you give me two vectors, U and V, so I'll take U, we'll call it U1, U2, those are the two components. V is V1, V2. If you want to add the two together, all you do is add the components. Take those two components, add them together. Take those two components, add them together. And whatever that number is, that's your new vector. the new components. Subtraction is the same way, except you have to be careful with order, right? If I say you take away v, then I'm going to do that minus that, right, first, and then I'm going to do that minus that. The other way around, you would have to switch these orders because subtraction is not commutative. In three-dimensional space, it's the same thing. You want to add two vectors, you just add up all their components. If you want to subtract the vectors, you subtract the components. Scalar multiplication. What happens if you take a vector and you multiply it by a number? When we see the word scalar in this class, scalar means a number, like a real number, constant. So let's say we're given some vector and we're given some scalar value c, and we're asked to multiply that c times the v. How does it change the actual shape of the vector? Well, it turns out it's a very simple process, a process that happens. If the absolute value of c is bigger than 1, so if that number that we pick is bigger than 1 absolute value-wise, it's going to stretch the vector out. If the absolute value of c is between 0 and 1, then it's going to shrink the vector. And if the value is negative, it's going to flip it over and point it in the opposite direction. So here's an example. So right now you see this vector v, and then the red vector so there's a black vector underneath this, you can't see it. The red vector is right on top of it. These are the same vectors. That's v and that's v. Now what I'm going to do is I'm going to have the computer scale v. I'm going to have it multiply it by a number. So I'm going to have it double. Let's have it double v. So this is a 2. Sorry, you can't really see it very well, but that's twice v. So is it pointed in the same direction? Yes. Is it longer? Yeah, right? It's twice as long. So all it did was stretched it out because that number in front is, the absolute value is bigger than 1, so it stretches it. If I do 3v, it's 3 times as long, right? 10v, it's 10 times as long. What if I do half of v in front of it? It's going to shrink it, right, to half as long, right there. Same direction, right? Half as long. What if I multiply by 0? What do I get? The 0 vector. You don't get 0. You get the 0 vector. If you multiply this vector v by 0, you get the 0 vector. Now, what happens if I go negative? It's going to flip it over, right? It's going to flip it and point it in the opposite direction. So what we're looking at there is negative v. This is v. That's negative v. They have the same length, don't they? Pointed in opposite directions, though. If I do negative 2v, it's going to be twice as long, but pointed in the opposite direction. Questions on that? Okay. Definition, parallel vectors. This is something that most students, like, when they see it the first time, they're like, okay, that's not the way I thought it was going to be. Seems a little odd. Any two non-zero vectors. So if you give me two vectors, as long as they're not the 0 vectors, okay, as long as these are not the 0 vectors, then we will say that these two vectors are parallel if and only if what? Well, we would think that it would be they're pointed in the same direction, right? That the arrows are pointed in the same direction. That means parallel. That's what we would think, right? That's not what the definition says, though. What does the definition say? They're scalar multiples of one another, which means that they do not have to point in the same direction, but they have to point, I mean, they could point in the same direction like that, but they could also point in opposite directions as long as they are both on the same like line, right? And these are still considered parallel. So like that, yes, they're parallel. And I can move them, right? Move them around, they don't have to be. So if I do that, they're both pointed that way, those would be parallel. But if I switch the direction of this one, it's still parallel. Scalar multiples is what is required to be parallel. So I'm going to give you a quick example on the board here. I'm going to ask you if these are parallel or not. Are these vectors parallel? I know for a lot of you that have seen vectors, I'm sorry, just hang in there. Are these parallel? Do you have an answer?
I have a question.
Yes.
What does scalar mean for scalar multiples?
Scalar multiple means that there's some number that you can multiply one of the vectors by to get the other vector. Which is why I want to do an example so everyone understands what that means. So the question here is, are these parallel? That means, are these scalar multiples of one another? That's all we have to check. So is there a number that you can think of that you can multiply this vector by to get this vector? No? Well, you first have to turn the -4 into an 8. How would you do that? Multiply by 2, right? So multiply this by 2. Sorry, not 2, -2, right? -2 times this would give us this. But now that -2 has got to work for all of them. Does -2 times this give us this? Yes. Does -2 times this give us this? No. What would have made this parallel? Had this been positive 2. Now they're parallel. All right? So the answer to the previous one is no. Here the answer is yes. You know, this would be yes. Why? Why, you ask? Because if I take -2 and multiply it times -4, 3, -1, I would get, as a result, the vector 8, -6, 2. So when you do scalar multiplication, what you're doing is almost like a distribution. You're like multiplying it through to each of the components. And that's what the new vector becomes. So that's the scalar multiple, right? That's the scalar multiple. Is that clear? Okay. What do y'all think that is? Do you think that's wiring? Do you think that that's bad projector?
All of the above.
All of the above? I don't know. I mean, I think last time, did it do this last time? I don't remember.
No, it was just shaking.
It was just shaking, right? So I'm wired in a different way. So I didn't bring my long HDMI. Next time I'll wire in the way I did before, and we'll see if we have the problem still. All right, so now magnitude of a vector, or length of a vector. So whenever you have a vector, right, it has to have a length, unless it's the 0 vector, it's the length of 0, right? The magnitude, that's a new word for us. The magnitude or length of a vector in two-dimensional space is denoted with like an absolute value bar around the vector v. So if someone gives us a vector v, which has as its components v1 and v2, if we want to know what the magnitude of it is, then here's the definition. It's the square root of the sum of the squares of the components. And that comes from like a Pythagorean idea. It's like a Pythagorean if you draw a right triangle. It's kind of like your a squared plus b squared equals c squared. So if you're solving for c, you have to take a square root. So it's the same sort of principle. Do I need to draw that out, or are y'all okay with it? All right? Okay. And then in three-dimensional space, it's the same formula, but now you have to add the third component in there as well. And that goes back to last class. Remember when Miranda? Was it Miranda? Miranda was holding, right? And we were doing like two right triangles to kind of verify that distance formula. It's the same idea that we should have three pieces to it now, right, into this. So I have an example for us to make sure we kind of can compute this. And I want to do example 4. All right, so I give us two vectors, v and u, right? Let's do part A. What does the vector v take away the vector u? All right, well, by definition, what I'm supposed to do here is I'm supposed to take this one and subtract this one, right? Take this one and subtract this one. So I'm going to take the first component of this one, 2, and take away what? -5. So it's going to be 2. I'm going to take away negative 5. And then I'm going to do 3 and take away 7. And then negative 5 and take away negative 2. And that should give me a new vector. That new vector is 7, right? Negative 4, negative 3. Okay, that's the vector v minus u. Now, what is the vector u minus v? We have two options here. We can actually compute it or just flip the signs. Like we know that it's that vector but pointed in the opposite direction. What does it mean to point in the opposite direction? That means it's a scalar multiple. You multiply by negative 1, it flips it over, right? So if I just multiply that by negative 1, I get that. Part C. What is 4 times the vector v? That's a scalar multiple. What's 4 times the vector v minus 3 times the vector u? 4v minus 3u is 4 times, watch the way I write this. 4 times v, I'm going to write the vector v, minus 3 times the vector u. The vector u is negative 5, 7, negative 2. Okay, so that's 4 times v minus 3 times u. How do I do 4 times v? It's like distribution, right? It's not truly distribution because you don't have addition and subtraction there, but it's basically the same principle. So it becomes what? 8, 12, negative 20, right? Right there. And then minus. Now here we have to make a decision. Do we want to keep this as a minus, or do we want to distribute it through as a negative and change it to a plus? What do y'all want to do?
Keep the minus.
You want to keep the minus and pass a positive 3 through. Okay. Keep a minus, and now I'm using a positive 3 that's going to go through here. So negative 15, 21, and negative 6. Do I have any questions up to this point what I'm doing? I mean, come on, man. I'm just out of curiosity here. I'm going to see if I press the power on this, what happens. Or you know what? I'll do this instead. Y'all go ahead and subtract those two vectors. I'm going to bypass this. It might actually be my cable's bad, because I am using a different cable. All right, let's see if that stays stable. Any bets on that? While we got this little downtime for a second, is there anybody in here who's pretty proficient with Fusion 360? Do y'all know what Fusion 360 is software? No? Man, I'm trying to find a student who knows a whole lot about that software. I'm stuck on something in it. All right, let's get back to this. So here, what are you going to do here? You do 8, take away negative, right? So that should be 8 plus 15, which is 23. And then you have to do 12, take away 21, which is negative 9. And then you have negative 20, take away negative 6. So add 6, you get negative 14, right? Y'all got that? Okay. All right, so we've answered part C. Now part D, and this is where you get your calculator out. Because for part D, we want the magnitude of this vector right here, of the vector we just got. And so by definition, for part D, the magnitude of 4v minus 3u will be the square root of what? each of these things squared and added together. So we have 23 squared plus negative 9 squared. The negative's not going to matter, but I'm putting it there anyway. Negative 14 squared. So whatever that is, right, is going to be the magnitude of that vector. We could get a decimal approximation, or we could use an exact answer and just leave it as like root of whatever. I don't really care at this point. What we're, that's not that important. The important thing is us being able to use that formula. Any questions on that? Did anyone do it? I see some calculators coming out. I'll wait. So 529 plus 81 plus 196, square root of that, and then whatever that is, right? Do y'all want to do it, or it's just, yeah, that's. All right, let's keep going. All right, we have an important vector. Actually, it's not a specific vector. It's a property of some vectors, and that is what are called unit vectors. Unit vectors, a unit vector is any vector that has a length of 1. If the length of the vector is 1, it is called a unit vector. That's it. So as you might imagine, there's infinitely many of them, aren't they? What's, I guess, the most important thing to understand with this idea of unit vectors is that if I take any vector, see this blue vector has some arbitrary length, direction. No matter where I put this vector, no matter where I put it, do you agree that there is a red vector that points in the same direction that has a length of 1? So for any given vector, there is a unit vector that points in the same direction, right? As long as this vector is not what? The 0 vector, right? Well, okay, so what if it's less than 1? What if the length of it's less than 1? Is there still a vector that is pointed in the same direction with the length of 1? Yeah, it's just longer than it, right? But there still is that vector. So for any given vector, there is always a vector pointed in the same direction of unit length. That means we should be able to find it, right? Like we should be able to find that red vector. You give me an arbitrary blue vector, I should be able to find you the red vector. Yes? Okay. Let's see. I think we might be able to do this together as a group. Let's say I give you this vector in blue. Let's call that vector up there. Let's call it V is the vector V1, V2. I would like for us to see if we can find the formula that gives us the vector that points in the same direction as that vector, but has a length of 1. And we're going to do this arbitrary, right? I'm not going to give you specific values. So can somebody tell me something very important about this red vector? The length is 1. Okay, that's going to be useful to us. We're going to need that. It's a scalar multiple of that vector, right? Which means, let me write that down. If this is the vector v, right, that's the vector v, this vector right here is some scalar multiple of that, right? I don't know what the scalar is though, right? But let's see if we can't deduce what that scalar multiple has to be. You're thinking of the formula. I think you've probably seen the formula, yes? No? No? So what are you thinking?
Well, you got to take a component and divide it by itself, right? If you're trying to get to 1, I mean, if you divide the component by itself.
We're not trying to get that to be a 1. Okay. We're trying to get the magnitude of it to be 1, right? But you're on the right track. Okay, how long is this vector? I don't know, right? It's something, right? Let's say that this vector was 10 units long. What would you have to do to shrink it down to have a length of 1? Divide by 10. What if it was 5 units long? What would you have to do to shrink it? Divide by 5. What if it was 1,000,000 units long? What do you have to do? Divide by 1,000,000. What if it was half a unit long? what would you have to do? Multiply by 2, right? Or divide by a half, right? So doesn't it look like all we have to do is take whatever this vector is and divide it by its own length? That's the formula, okay? So to find this unit vector, let's call this unit vector, let's call this u for unit vector, okay? U, this unit vector that points in the same direction, should be, how do I say that? I want to scale it, right? I want to scale it by 1 over its length, right? Like we said, if it was 10 units long, we want to divide it by 10, scale it. So I'm going to write it this way. I'm going to take the vector v1, v2, and I'm going to multiply it in front by a number that kills off its length, so it's 1 over the magnitude of v, right? We said if the magnitude of v was 10, we want to divide by 10. This would divide by 10, wouldn't it? If the magnitude of v was 5, 1 over 5, that would scale everything down. Do y'all see how that works? Yes?
Why could you not write it as the vector v divided by the magnitude of vector?
You could. You could write, this is exactly the same as this. I think this is what you're asking.
Yeah.
Okay. What's important for us to understand in all of these notations is that this is a number, right? That's 1 divided by the length of a vector is a number. So this is a number, this is a scalar, sorry, and this is a vector. So how do we multiply a number times a vector? Well, we're kind of pass it through, right? This is another notation for that. Just be careful that you aren't trying to like cancel these out and make this like a 1, because it's not. This is a vector, this is a number. Vector, number, vector, number. You can't cancel anything out. Y'all still good? All right, so now what I'm going to do is, let's see if we can actually figure out what this is. Do we have a formula for this? Yeah, that's the square root of v1 squared plus v2 squared, if we're in two-dimensional space, right? That's what that is on the bottom. And we have to multiply that through to v1 comma v2. This is a number. 1 over that, right? 1 over the length is a number. We're going to now pass it through, and we will have a formula for finding the unit vector that points in the same direction for any vector, period. So pass it through. We're going to get a new vector. It'll be v1 over the square root of v1 squared plus v2 squared, and then v2 over the square root of v1 squared plus v2 squared. Now, most of the time, we don't go try and memorize this formula. What we try and memorize is that formula or this formula, like this or this. This is the one most of the time you're going to see, right here. But that's more of a generic, like we can actually just plug things into that. Now, I said it seems like this would be right? Like if it was 10 units long, we would divide by 10, right? And y'all agreed with that? No one disagreed? That's how we came up with this? How could we convince ourselves now that this is, yes, in fact, a unit vector? I mean, we think it is. This should be a unit